Hello and welcome to our design project presentation on reconstructing the monsoon steel furnace. This project was a collaborative effort between two teams, research group and the prototype development group, which is us. We are team G04 and in this video we will take you through our research, design process and the final prototype. For a steel furnace specially developed to withstand tropical monsoon conditions, let's begin with a quick overview of what we will cover. We'll begin with the background and the problems with traditional furnaces in monsoon conditions. Then we'll go over our goals, research and how we develop the design and prototype. We'll also cover the challenges, sustainability and the impact of our work, ending with how our design improves on older models. Sri Lanka's rich metallurgical heritage, evident in sites like Sigiriya, Anuradhapura and Samanalawa, dates back to 3000 BC and includes the world's first wind-driven iron smelting furnaces. These use natural airflow and local materials to produce high-carbon steel. Building on this legacy, our project reconstructs a furnace adapted for modern monsoon climates, merging traditional design with contemporary materials and CAD technology. By addressing challenges like humidity, corrosion, and thermal inefficiency, we aim to create a sustainable, durable, and efficient model to tropical regions. Traditional steel furnaces face significant challenges during monsoon seasons. The high humidity causes them to corrode quickly, while moisture infiltration reduces heat retention and increases fuel consumption. In ancient times, the furnaces must be broken open to extract the steel, making them non-reusable. These issues led to frequent breakdowns, resulting in high maintenance costs and operational delays. Project is focused on addressing these core problems with a more durable and efficient design. To address these problems, we established three main goals. We aim to build a physical prototype that accurately represents a practical furnace layout. We developed a detailed 3D AutoCAD model to help visualize and refine the design. Finally, we focused on proposing and integrating key modifications and modern improvements to enhance the furnace's durability, usability, and environmental performance. In developing our design, we identified key requirements for adapting the furnace to monsoon climates: resistance to moisture and corrosion, effective thermal insulation for temperatures up to 16,000 Celsius, prevention of water ingress, stable airflow for combustion, and a safe steel extraction method to preserve structural integrity. These needs were assessed during CAD tools, technical blueprints, and refactoring material data. During the design development stage, we created a detailed AutoCAD model of the furnace. This digital representation helped us visualize the structure, refine the layout, and evaluate the spatial relationships between key components. The model served as a critical step in translating our initial concepts into a practical, buildable design and ensured greater accuracy before moving on to the prototype construction. This cross-section view of our furnace design gives a detailed look at the internal structure. It helps us understand how different components are positioned and how heat and airflow move within the system. To get a clearer understanding of our furnace design would look and function in practical, we built a small-scale prototype using styrofoam, paper pulp, and wood. This physical model allowed us to carefully study the overall structure, examine how the internal parts were arranged. We proposed several improvements to enhance the traditional furnace model. First, modern refractory materials were introduced to ensure better heat retention and consistent high temperature performance. A dedicated steel extraction port was added, allowing safe and repeatable removal of steel without damaging the furnace. To address moisture issues, the design includes an elevated base, sealed vents, and the use of corrosion-resistant materials. We also optimized fuel placement and internal airflow to improve combustion efficiently. These design upgrades were meant to significantly improve the furnace's performance and durability in monsoon conditions. In addition to structural changes, we also proposed several advanced features for future development. The inclusion of temperature monitoring tools such as thermocouples to track the internal conditions, a dedicated drainage or ash collection zone to prevent blockages and support clean operation, consideration of seasonal wind variations, and finally, safety enhancements like pressure release reduce overheating risks. These proposals aim to make the furnace smarter, safer, and more adaptable over time. Like any project, ours had its limitations. One major challenge was that our prototype is non-functional, as it was built using basic materials that cannot withstand high temperatures. Because of this, we couldn't directly test how the furnace would behave during actual operation. Instead, we had to make assumptions about how the real materials such as refractory linings and metals would perform under extreme heat and stress. Additionally, due to limited time and resources, we were unable to carry out detailed environmental simulations. Some system features were also simplified to keep the prototype practical and manageable. These limitations point to important areas for future testing, validation, and improvement. Sustainability and long-term usability were central to our design approach. The furnace is designed to last over 5 years with minimal maintenance, reducing material waste and rebuild frequency. It promotes safe steel extraction, preventing structural damage and making repeated use possible. Environmentally, our prototype does not emit gases. Future models can integrate emission controls like filters or carbon capture systems. In terms of social impact, the furnace supports small-scale steel production in rural or monsoon-prone areas, boosting safety, reliability, and local resilience. To conclude, we successfully designed a conceptual monsoon-resistant steel furnace that blends traditional knowledge with modern engineering. We developed both a 3D AutoCAD model and a physical prototype, validating our ideas visually and spatially. Our focus was on durability, efficiency, sustainability, and safe steel extraction. Also, this project gave us hands-on experience in design thinking, collaboration, and practical problem solving as an engineering context. This project was a collaborative effort by our team, Design Group Number 4. Thank you for taking the time to watch our presentation. We would also like to sincerely thank everyone who supported us throughout this project.